players or various objects I want to bring together in today's lecture are probably unfamiliar to most of you. So when we talk to Liouville quantum gravity surfaces or conformal loop ensembles, maybe, stable processes, that's probably more of a known to most of you. So my goal will be more to try to give you, use the fact that I want to tell you about something new, ongoing, which is, by the way, joint with Jason Miller and Scott Sheffield. But I want sort of to use this as an excuse to give you some introduction also to the main objects that have been developed in recent years and try to explain you why they are interesting and why they are important, and then probably try to just state one result, and hopefully by then you'll see why it is intriguing, and maybe you'll feel it's nice, but it's at least surprising in many respects. So what I want to start with are basically introduce you three a priori, disjoint looking random structures that I think is good that you hear about them. And maybe the first one I want to say is this thing called Liouville quantum gravity. So Liouville quantum gravity, each time you give a talk with that in front of people like Fröhlich or something like that, they jump up and say, this is neither Liouville, this is nor quantum nor gravity, why do you call it like this? And then we say, well, this is not our fault. This is just the way the physicists started doing it and selling them. Sometimes they're quite good at finding good code words and three-letter acronyms for them. So you can erase that and say random metrics, right? So that's more or less, the way you as probabilists you would like to you want to think about it. And so you're giving yourself some space, so d-dimensional space, and what's going to happen very quickly is that we're going to be in 2 dimensions. So imagine we are already in a 2-dimensional space. You have a disk or a whole plane, a sphere, or whatever topological object you have in mind. And then you want to find what is a natural way to define a random distance structure on it. Okay, so the way you may want to think about it is, typically we know about if you have a domain which is simply connected, the Green's function, potential theory, Brownian motion, all this, we know is related to probability. And then you want to say what are somehow the fluctuations away from something like away from the Euclidean distance, something like that. And so, of course, as always, like in these type of questions, some people who were not doing probability theory had understood a number of things before the probabilists arrived and said, well, wait a minute, when you solve the Dirichlet problem, it has to do with Brownian motion, but the solution was there before. Yeah. So, and here it's a bit the same. You have one big name here is Polyakov, right? Who's this physicist in the theoretical physics in Princeton, and he had basically the idea of what was the natural way somehow to define, try to define a random metric structure in a domain. And the first observation you want to make is that one natural, simple way, and that's, very hand-waving, I'm going to say, in very introductory level. Maybe those of you who know more the precise details about them will feel that I'm cheating all the way, and I'm not hiding that. But a very simple way to define a random metric, say in a domain, would be to actually start with a random function. And if you have a random function f on your domain, then you can decide that if the function is positive, for instance, then you can start saying, well, this is the amount of petrol it costs you, or the maximal speed you can travel at point x will be f of x. And then, when you're given 2 points, the distance will be the shortest path, the quickest way to go from x to y. given the fact that you have the speed limit given by f of x in your domain, and that if you have a random function, positive function, then you have a random distance automatically that comes with it that is defined in this way. Okay. So and then therefore somehow defining random metric in this way and defining in a random function is sort of interconnected. And then the question is, what is the natural random function you want to choose? And what Polyakov realized, and that's not, you know, that was sort of in the air in the 1970s already, but that sort of was that you choose f. So you want this f to be a positive function. So the thing is, you take f to be the exponential of some constant time this thing, which is called, this is a Gaussian free field, right? A Gaussian free field in 2 dimensions. So what is the Gaussian free field? In some sense, I'm not going to give you the definition with Green function, covariance, and Gaussian fields. The way you want to think about it is Brownian motion can be, you know, the scaling limit, or Brownian bridge can be the scaling limit of random walks that have plus or minus jumps, and it's sort of the uniform measure on you know, simple paths from a point to another, where that are allowed to go up and down by 1. Okay. Now, if you are in 2 dimensions, the natural generalization would be to say something like the solid-on-solid model or something like that, where basically at each point in the plane or on the lattice, you have a height which is integer valued, and you have the constraint that 2 neighboring points can be at height plus, you know, the difference between the height of 2 neighboring points can be just plus 1, minus 1, or 0, right? So it's just a natural fluctuation, like simple random walk will be the natural random curve. This sort of solid-on-solid model will be the sort of natural, you know, random surface you can draw, which has the constraint that, you know, nearby points have to be at nearby heights. And when you take the limit, when, you know, you have to take the appropriate scaling limit, what you get then is this 2-dimensional Gaussian free field. Now, there's one point, as we know, that when we teach about Brownian motion, we know, you know, we give the definition of Brownian motion, and we say, well, by the way, there's something we have to prove, that Brownian motion is continuous, right? And this is a bad surprise because it's not totally obvious, and to prove that Brownian motion is continuous. Now, what happens is the Gaussian, you know, in these 2-dimensional models, what happens is that, you know, they are much more constrained, right? The fluctuation of this sort of tent, you know, because you are, you know, pulled down at not only at 2 ends, but at, you know, each point can fluctuate much less. So the fluctuation of this solid-on-solid model is very slow. It doesn't you know, fluctuate like square root of n, like a simple random walk. It will fluctuate like something like square root of log n or something like that. So physicists, you know, who work on this, they say, well, I know the solid-on-solid model. I do my experiments. I can tell you it's flat, right? And they're right, because square root of log n, you know, is very small and actually, you know, could be quite close to 0. So unless you have a system which has, you know, so many particles that you're not able to, that it's not possible. So in some sense, this you know, square root of log n fluctuation scaling limit is not something you actually see really in physical model. It's a bit like a mental, you know, probabilist thing that you take a limit and divide by square root of log n, and then you. But the thing is that, therefore, in order to see something macroscopic, right, you have to stretch in the horizontal direction much more, right, in order to see something fluctuating, because it fluctuates much less. You have to magnify by something huge in order to actually see some fluctuations. That's what you are doing when you get the Gaussian free field, and the result of it is that this Gaussian free field, you are stretching so much, well, it's not a continuous function. It's not a, you know, a function. It's not continuous anymore. It's not a continuous function from the plane onto the real point, right? It's something which actually only makes sense as a generalized function. Okay? So you can make sense what the average height is in the domain, things like that, but the height at a point doesn't make any sense. So that's sort of, you know, this type of Vs. And now, of course, we all learn that if something is a generalized function, it's strictly forbidden. You get a very bad mark if you take the exponential of it, because you know, random generalized functions. I mean, generalized functions are you can make sense of linear operations, but when you start multiplying them and do things like exponentials, that's, you get in trouble. However, and that's not a big deal, it is possible to make sense of such an object, such a function, except that using the fact that our object is Gaussian. So code word, Gaussian chaos, things like that, renormalization, you can make sense of this sort of random function. And in order to do that, you have to do some renormalization operation. Which is involved, and I mean it's not very involved, but you have to, the definition of this involves a renormalization operation that has to do with typically what you can define, for instance, is for each point z, right? You can, gamma of z doesn't make sense, but you can make sense of what the mean value of gamma is on a small circle of radius epsilon around z. That's a nice Gaussian random variable, and so you can define gamma epsilon of z as a nice Gaussian process with a covariance finite Gaussian process with a given nice covariance function that you can define, and that would be the average value of gamma on the circle of radius epsilon around z. And then you can just take exponential gamma epsilon of z. Okay, that's makes sense, exponential of a number, and then try to let epsilon go to 0. And what happens then when you let epsilon go to 0, then this function here will, this will blow up, and you have to renormalize in a certain way, and so roughly what you want to do is something like exponential of this, right? This blows up when epsilon goes to 0, but you renormalize in by something like that. And this just has to do, the gamma squared over 2 is just the usual, quadratic variation of Brownian motion that we have in the game. So the point is that there's a renormalization operation that uses somehow some information about the metric of the plane that you're playing with, right? So it's epsilon. And when you say epsilon, that means that you have measured, the average value on the circle is something like, looks like more intrinsic, defined. You're not using the fact that it's epsilon or 2 epsilon, it's just the mean value of what you see there. But then you have this renormalization operation which involves epsilon to the power gamma squared over 2. Okay, so now the question is, now we have a good candidate for defining our random function, and that random function will define us something that will enable us to measure, the distances according to, but there's a big question, right, a big conjecture. A big open question in the field is to say, well, you define this, so this defines you a very weird and very, highly oscillating type of random function. Does it really correspond to a random metric? Right? Are you really able to say that this procedure that out of a function defines you a metric by taking the length of the shortest path, things like that? In that case, this thing is like oscillating. You should think this as f as being, both plus minus infinity everywhere, right? So there will be places where it costs you, infinite amount of petrol to cross, but there will be very thin fractal structures, and then you will have sort of motorways, maybe that, percolate or don't percolate, where it costs you much less, but they will be like very windy fractal curves. So the question is, how do you make sense of the actual metric? Can you show that it is well defined and something like that? So there's just one value of gamma, which happens to be square root of a third, for which Sheffield and Miller have a long sequence of papers that are under review, and referees are struggling, but where it's pretty clear that the strategy is correct, and that in that case this metric that you could define in this way is exactly the same, and then, just for the record, as the random metric that appears as a scaling limit of planar random maps. And I'm sure some of you have heard the talks by Le Gall, Mirmont, and others about the fact that discrete structures in the scaling limit, when you take the metric distance associated to graph distance, rescale converges to some object called the Brownian map, and that should be the same one as the one that appears from the continuous world perspective here. Okay, that's one object. Now, the important thing is that what is a random surface, and that's something, of course, that we don't like so much, is that I'm giving myself a domain and one of these functions here, right? Maybe an f here. And I know that the Gaussian free field gamma behaves nicely under conformal transformations. That means that the Gaussian free field gamma is when you map it, when you have a domain and you distort it by a conformal map onto some other domain, right? Just an angle preserving one-to-one map from D onto this other domain. Then the image of a Gaussian free field here becomes a Gaussian free field there without any rescaling operation having to be done. Now, and this has just to do with the fact that Gaussian free fields related to the Green's function, which related to Brownian motion. Brownian motion is conformal invariant, so it's no problem here. However, when you do f is obtained by the renormalization operation from the Gaussian free field. What happens is that you end up here with a new domain D, and now you get f tilde, right, which is the image of the something like that, the image of f under this conformal map. And what happens is that because of the renormalization operation that you have here, the f is not conformal invariant, right? Because when you map f, then the circle of radius epsilon becomes a circle of radius epsilon phi prime of z, and therefore the moral of the story is that when you map this conformally, basically what happens is that gamma, sort of the f tilde, okay, maybe I'll just write it in terms of gamma. You start with a gamma here and you define f. Now you look at what happened to gamma tilde here that defines the f tilde on the other side. What happens is that everything plays a role as if the surface that you're looking at, when if you stretch it, right? If you stretch it, it goes up. And if you compress it, it goes down, right? So the idea is that you will have something like gamma tilde will be something like the image of gamma, plus there's a constant, which just have to do with the gamma squared over 2, times log of phi prime. Okay? So there's a special rule that tells you how these, when you're looking at these random metrics that are defined out of the Gaussian free field, when you apply conformal transformation, there's a special rule that tells you, if you compress, the surface goes up, and if you delay, do the opposite, then it's sort of the surface goes down. So in some sense, it tells you something about, if you compress, then it will cost you more to travel there, and if you will cost you slightly less. So you're an extra bonus in sort of a conversion operation. So a Liouville quantum gravity surface is something which is defined to be in equivalence classes of domain and function f, and equivalence classes modulo this equivalence. Okay? So you can define it in a domain, and we have a certain function, or it could be, it can be sort of, incarnated. The same random quantum gravity surface could be incarnated everywhere. So in some sense, you should think as one of these quantum surfaces, it's something that lives in some abstract space and is not yet embedded, right? You can then choose how to embed it in the plane, or which domain you choose to embed it in later. Okay, that's the fundamental thing. Now, when you define these objects, very often when you apply, when you're using very, very slow here, when you use Riemann's mapping theorem and probability, you want to define probabilistic structures, you want to find a way to define object with as little additional marked points as possible. So for instance, when you define a Brownian motion in a domain and you want to say Brownian motion conformal invariant, usually you say I take a domain, I take a point, I start a Brownian motion from this point, I take the conformal image, and then I have a Brownian motion started from the image point. So by doing that, you're choosing a domain and a point. Okay, and then it's a trajectory started from that point. There's the thing about Brownian loops that are nicer in some sense, because the Brownian loop measure is something that doesn't involve choosing a point. It's just defined in the domain. And then you are looking at a random structure that didn't involve choosing anything in your domain. It's just a random structure that you have there. Now here, for those models, the question is, what are the natural Gaussian free fields, because I haven't said anything about Gaussian free fields and their boundary conditions. What are the most natural ways, variants of the Gaussian free field that you can choose in such a way that these equivalence classes of domains do not involve any marked points? And here the idea will be there are two very nice Liouville quantum gravity surface. And they are called, one of them is the quantum disk. And the other one I might want to call the quantum half plane. And I don't want to enter in the definition of these objects. I didn't learn my... okay. I don't want to enter into the details here. Just want to say the quantum disk is the natural choice of equivalence classes of random structures in a simply connected domain, which involve no choice of marked point. Okay. I hope I will get you some concrete incarnation of what that object is a bit later. The quantum half plane, as we know, the half plane, there's a very special marked point on the boundary, which is infinity, and all the others seen from infinity are basically the same. They are the points on the real line. So the quantum half plane is the one where you choose one special marked point, and all the others are basically the same. Okay? So if you want to think about it, you can think, what is a Brownian measure that you can define in the quantum half plane? Well, you can say it's the Brownian excursion coming from infinity going all the way back to infinity. That's something that looks like a structure that just involves the choice of one starting point. Here you say Brownian loops just involve no choice of starting point, right? It's just an analogy you can have in mind. Now, there are two things that are important that I want to emphasize. The quantum disks, there are objects like that, and they have a very special property. I mean, all these structures have the property that when you look at the boundary, you can look at whether the boundary of the domain itself has a length that is defined by the object that you have there. Right? That would be the boundary length of your quantum surface. And as you might expect, a quantum disk has the property that the boundary is finite length, and the quantum half plane will have the property that the boundary actually has infinite length, namely that any neighborhood of the special marked point, infinity has an infinite length, and otherwise the boundary locally is finite. Okay, so now the second player in our story I want to tell you are the conformal loop ensemble. So forget about this scary thing. I started with the most scary one. Now I want to say something a bit more concrete. So now I have a simply connected domain, a domain D, and I want to look at the scaling limit of lattice model interfaces. So for those of you who know about the Ising model, they might just think of the Ising model being one example that gives rise in the scaling limit to one of these conformal loop ensembles. So these are objects that look like random objects that look like that. And that are defined in any simply connected domain D. And they have a number of properties, one of them being that this random picture that you get here is conformal invariant. Right? So if you apply Möbius transformation, then you have another one, but its distribution is the same as the one you started with. And there are a couple of other properties, axiomatic properties that you could put down that actually characterize them. And that's sort of older stuff we had with Sheffield. That explain basically that they are the only possible candidates for scaling limit of certain classes of discrete models that would give rise to conformal invariant structures in the end. And maybe I'm not going to go too much in that, but there's a one family parameter of those, kappa, and it just turns out that the way this is written usually is that this kappa value is between 1/3 and 4, because this kappa value has to do with the definition of SLE that is behind the scene, and the fact that each of these curves here will be like SLE type curves. So what happens is that for each value of kappa, you have one random object like that, which is called a conformal loop ensemble. And just for the record, one way to characterize uniquely these objects is to say they are conformal invariant, and they have the property that if you cut out, without knowing what is in here, you just take your scissors and cut your domain, become smaller, you cut this away, and you view these things as holes, like a sponge, right? You cut it in the middle, and now if you cut the sponge into the middle, then then these are holes. So now you have a new domain like that. You take it, you have a new sponge with on the boundary you have pieces of holes, and now what you can do is that the law of this object here, now this is a simply connected domain. You can map it back, stretch it back by Riemann's mapping theorem back into the unit disk. Okay. And what you need to have is that the law of what you obtain when you map what you have here back onto the unit disk is the same as the one you started with. Right? And that's something, if you believe that these things are interfaces, and you have conformal invariance, this is something you believe is true, and there's this theorem that says if you have a random structure that has these properties, then it is one of these conformal loop ensembles, and we know exactly how many there are. There's one for each value of kappa. And we know more or less everything about them, what the fractal dimension of all these loops and how they are defined with each other and so on. In particular, one very nice, so the way you want to think about it is these are the random fractals that nature in 2 dimensions is able to produce. That's, a very, provocative way to say it, nature will not produce the Sierpinski carpet. Right? Because you have to be very well organized to do exactly, find the middle, It will not find, the Cantor set. You could say, well, in Cantor set will be replaced by the 0 set of Brownian motion or something like that. That would be like, or stable range of a stable subordinator. That would be the natural way to want to say that's and here these are the 2 dimension, the version in 2 dimensions. Okay, so these are the way you want to say it. And one thing we did with Scott and Jason, I guess the paper is 2017, but it was still a couple of years ago, that inside each of these sponges, one can make sense of a very special path, right, that goes in here, and that we can interpret as critical percolation within the sponge. Right? So it's a fractal set, so most of the places there are empty. But still, if you put enough pressure, you say, well, more pressure, maybe you are able to define something like, how water could try to infiltrate the sponge, and then what is the boundary of the wet part here. And that would be this green curve. So we could define this structure, this green curve here, that you can really view as the way to, how you're going to infiltrate the percolation thing within this natural random fractal. So this green curve has the property that when it sees, when it sees a hole, right, it's sort of going here, and here on this side is wet, here is dry. Okay, so when it sees a hole, this green curve will have to bounce to leave the hole to the right because the hole is empty, it's dry anyway. Won't help you to get, okay? So this green curve moves is a curve that you can also view dynamically that is growing into the inside of the domain. As soon as I touch a hole, I attach the hole. I could discover the hole, but the green curve will have the property like percolation curves do, that it will bounce on itself. It will sometimes bounce on the boundary, and so on. Okay, that's our second player here. Now you see that this exploration object, this sort of the way to explore with this percolation structure, is sort of reminiscent with this axiomatic thing I said here, because you say you can view your exploration thing like cutting with scissors also. And somehow you would expect that if you explore dynamically what you get here by adding all the holes that you have discovered, the law of what remains in front of you will still be the law of conformally speaking, the law of a sponge that needs to be discovered. So, okay, that's just this thing here. And for those of you who have read those papers on conformal loop ensemble, they might know that really this plays the role of, is a little bit very reminiscent of a two-dimensional incarnation or version of what one-dimensional subordinators might be, or stable processes might be. Because each time you hit a hole, okay, it's like a jump. And the law of the holes that you have in front of you are conformal invariant. And so by conformal invariant, it means that there is some scale invariance there. So it's a bit like you're discovering holes, Poisson point process of holes that are in front of you that you're discovering. The jumps are scale invariant and or conformal invariant that replace the scale invariance here. And so these structures here are in some sense reminiscent of structures that you can define in one dimension as stable subordinators. Okay, now the third third object I want to explain very briefly is, and that's a good old friend of ours, which has to do with stable processes. And maybe also stable trees or tree-like structures as a more German, familiar subject to some of you here, which are fragmentation, stable fragmentation processes. So here, what I want to emphasize is, well, maybe I should just before I go there, I want to emphasize one thing with my green sponge here. If you follow this green thing here, sometimes, the green percolation path will hit a loop, and then the loop will be attached to the left-hand side. That means that seen from this point, when you hit this loop, then the domain, the sponge left is, suddenly there was a jump, it became smaller. Sometimes the green curve, can do this and hit this hole again. And when you do that, then you disconnect, then your sponge is divided into two pieces, this piece here and this piece here. So then you throw away a piece of your sponge. And a third thing is, of course, that this one could, for instance, touch the boundary on this side, in which case, again, you're cutting your sponge into two pieces, so you have this one and this one, so you have to throw away all this one. So somehow seen, when you do this discovery along the percolation curve of your sponge, seen from a marked point, you have three different things that can happen. Either, the domain, gets this, but then the boundary of the domain gets larger, the domain gets smaller, or the boundary of the domain here such gets a negative jump because you cut away pieces of the boundary when you hit them. Okay. Stable processes, as we know, that's just, you take a Poisson point process on the positive time where jumps of size x will appear with, something like that. That will be the intensity of jumps. A jump of size x will appear with a probability that is proportional to that. And, it will appear with time, so you could say dt like this. That's the sort of the intensity of appearance of jumps of that type. And as we know, that would be a stable subordinator. If alpha is smaller than 1, then you can make sense of that. And what I'm interested here are, when alpha is larger than 1, which is the case where you need to do something because the total sizes of all the jumps are, the total, is diverging. So you need to do some renormalization operation, which is called, in order to make sense of what the totally asymmetric stable process of index alpha would be. So I'm not going to, that's what I'm telling you is like, it's the usual, Ito calculus thing. You have something which has infinitely many impulses, so you have to do some sort of a subtract all these plus impulses. You subtract the average value to get something which has a, where the jumps are, positive jumps and negative drift. And if you do that correctly, so an average is 0, then the plus and minuses infinity will compensate, and you're able to define, which is sort of, you need a renormalization operation that tells you that we can define the totally asymmetric, so here x positive, stable process of index 1/2. So that's just a process, right? So the idea is, the jumps are positive, and then you have these, the way you want to think is something like that. You have positive jumps, a very, very strong negative drift, and the jumps are all over the place. They happen all the time, but the negative drift is actually minus infinity. But you do this in such a way that it actually compensates, and that in the end, because here you chose everything, so it has a scaling feature here, that the process you get here, xt, has the property that if you take x lambda t, is going to be equal in law to lambda to 1 over alpha xt. And I apologize if I got the 1 over lambda something. Maybe it's wrong here. I think it's fine. Okay? So that you have a scaling property that comes here. These are the totally asymmetric objects, stable processes. Now, there's one very nice variant that you want to use that's going to play a role here. Whoops. A natural variant, which has to do that you want to, if you want to think of these stable processes in order to be able to define something that is a little bit like a branching structure, reminiscent of what we had before. So there's a variant which is a very natural variant that you want to have if you want to imagine you want to have these type of objects, but you have a constraint that you want that x never becomes negative, because x should be something like a length. So the process x here in that picture, it will have this negative drift. Sometimes it becomes very negative, very positive. It will oscillate. It doesn't have, anything. It's not a subordinator because it has the negative drift. It can become negative. So the important variant that you have here is that imagine that I have x, right? Now, what I'm going to say is that instead of saying that it jumps to x plus h or jumps to x minus h, x can split, right, in two pieces. The first pieces would be like I split into x plus h, and you'll see in a moment why I'm doing that, right? And that you do it with a rate, which is the one that you have here, over dh over h to the alpha plus 1. And the other option would be, well, I split into x minus h, right? And then, of course, the idea is when I split, this guy and this one, these two will evolve independently according to the same type of structure. And here, of course, there's always the question, here it's clear this one is larger than this matrix one. So you identify them well. Here it's not so clear, who is going to be called x minus h and who's going to be called h. So you could say something, the rate here will be the h over h to the alpha plus 1. And then here you can say something like indicator function of h smaller than x over 2, right? So that this one is the larger of the two. It's just, the way to rename them. Now, that would be more or less this, but when you do this, then, this positive, negative thing it doesn't look like so nice. So one very natural structure you want to put, and I hope you will, I'm not going to explain to you that why, but it's sort of really the natural thing you want to do, because now you can view this 1 over h to the alpha plus 1 somehow as the partition function of the guy size h. Okay? So if you want to view this pair, right, as a pair of two independent things, you want really to put here on top of it, x plus h to the power alpha plus 1, and here x minus h to the power alpha plus 1, because then, the rate at which you split is going to be given by, the product of the two partition functions of the two independent things that you are going to have in mind in front of you. And so somehow this thing here will be like playing a bit the role of the energy of the structure one you did split, and therefore you can time change this by something like that. Okay? And if you do it in this way, then it's really something where, a nice, it looks very much like a usual, dynamics of a statistical physics system where, the probability of a jump is going to be given by, the ratios of some energies of after the jump and before the jump. Okay? Now, when you define these things, there is still, and I have sort of cheated you now a lot. It is that I defined you here the one with only positive jumps, and now suddenly here I'm introducing negative jumps. So you say, so this object here, right? You can view it as the sum of the one with positive jumps minus a certain constant time, an independent copy of the one with the negative jumps, right? This will be not the totally asymmetric one, but a biased one. And so these objects here are characterized, and now comes the important value here. There's another constant here. Let's call it lambda. Okay? And lambda is just the rate, between the positive jumps and the negative jumps. Right? So it's not a totally asymmetric stable process anymore. It's an asymmetric one which has a weak asymmetry between the positive and negative jumps. And it has a constant lambda, which is sort of the intensity of positive jumps where there's negative jumps. Now, if this intensity is smaller than 1, you would expect that if you start from x and you let evolve this structure, there are more negative jumps than positive jumps, so the things tends to become smaller and smaller and split up, and eventually the thing will just die or go down to zero size everywhere. Okay, so now I'm ready to state the result. And in some sense, I'm not going to explain to you why, but in some sense it's a way to explain why all these quantum gravity structures that have been used here have so much to say also for the for the usual our usual friends like conformal loop ensemble or lattice models. And here's the result. So I take a CLE kappa, okay, in the disk, and take gamma, well, maybe I could here, square root of kappa, which is the value of gamma, usual quantum gravity disk, which is independent of the CLE. And you look at it, you embed it, you take the representative in the unit disk. Right, so I have here my sponge structure, and on top of it, independently, I use this fluctuating, metric that you define in the whole object here. Okay? They are independent. Now what you do is you explore this one via the green, exploration process that you want to you're going to explore in using this, the percolation picture that I drew, this green path that I drew to you before. Now what happens is that sometimes, as I told you, what is going to happen, sometimes you discover a loop to your right. What happens when you find a loop to your right is that just before you had explored this. So your domain that you were looking at just before, your sponge that you were cutting open just before, looks like that. Okay, and it has a certain boundary length. But when you discover a loop, okay, what happens is that somehow the new boundary length, gets this extra length of the loop. So the boundary length of the domain that remains to be explored here gets a positive jump that has to do with the length of the loop you're exploring. But the length in terms of Liouville quantum gravity length. Plus, of course, what is inside here, the loop, has this sort of, there's this iterative mechanism. So what you have inside here is again a CLE in here. Right? So you could continue exploring into there or exploring to the outside. So now you have two sponges, the small one in the inside and the large one to the outside. Okay? That's reminiscent of the positive jump that you have there. The boundary length x is split into two sponges, one with boundary length x plus h, that's this one, when you discover a loop, and one with boundary length h, which is the one inside. Now, when the green curve hits the boundary, as I told you, what happens is that now you're going to split your thing into two sponges, and now the previous boundary length was all this. Just before disconnecting this, the previous boundary length was all this object. And the new one is just, well, you cut x, the previous one was x, and now it's cut in x minus h and h, where h somehow is the smallest length between this one and this one. And the same is true when you disconnect to the right. So the big surprising feature is that the structure of the Liouville quantum gravity surfaces that are cut out by the green percolation picture, path in the CLE is a Poisson point process of Liouville quantum gravity disks. So here there's something very important, which is that what you find, the quantum gravity surface that is in front of you, the next one that's going to find, is independent of everything that happened to you before. Once you know its length, it's going to be a disk of that particular length. Okay? So in some sense, you discover space, and whatever you do, you're doing an IID. You know, it's like always, you're always having to discover a new disk. The disk might be of larger boundary or smaller boundary. So what I mean here is that if I stop the exploration at a given time, the law of the remaining to be discovered domain is a Liouville quantum disk independent of what happened before. Plus the boundary length evolution, so the jumps, so meaning the length of the disks here is exactly an asymmetric stable alpha. So what is alpha is for the kappa process. So there's a, what you see then is the sizes, the quantum sizes of the disks that you're discovering when you cut this open one after the other will be given exactly by the jumps where the alpha is here, but except it's this variant here. It's exactly an asymmetric, this variant, the previous variant. Right? And now you say there's just the one magic formula is what is the the asymmetry rate, what is the intensity of loops versus intensity, what is the intensity of things you cut out by seeing a loop, or the stuff you cut out by hitting the boundary. Okay? With asymmetry parameter, lambda, and it's just, it's our old friend lambda minus cos of 4 pi over kappa. So indeed, kappa has to be between, this asymmetry parameter has to be between 0 and 1. So kappa has to be between 1/3 and 4. So that, this cosinus now, the cosinus goes between -1, this guy goes between pi and 3 pi over 2, and therefore the minus cosine goes between 1 and 0. And indeed, what you get is that the whole description of the space that you have in front of you of this sort of CLE that you want to discover, one very, very nice way to encode it is to say that you equip it with an independent random metric. And if you equip it with the independent random metric structure that is given by here, I'm cheating because we don't know it's a random metric, we know it is the structure that I defined to you before. Then, when you discover objects in front of you, it's really like discovering completely IID structures, quantum structures that are in front of you. And the important feature here that you have to have in mind, so you see here we have a Poisson point process of these disks. We glue them together by, you discover according to that, and now there are deep complex analysis results that tell you that actually, if you are given the structure of the quantum disks that you have here, remember they're not embedded, the quantum disks. So what you discover is something that is not yet embedded. And the idea is that the way this one is going to, this disk here is, when you discover this here, the way this disk is going to be glued to the other disk by, in order to form the actual CLE loop that you are going to discover, the way it works is that the boundary length on the inside and on the outside have to match. Okay? So if you are given to you and in order for these two things to match, plus having conformal invariance, this is known in complex analysis under code work conformal welding operation, right? I know this one has a boundary length, this has a boundary length. You want to put them on the same space in such a way that the outer boundary of this one is somehow fits with the outer boundary of the other one in such a way that the lengths are exactly the same. And what happens is that usually you can only do it for smooth curves. These are fractal curves, but they are fractal but sufficiently disorganized that they are not pathological, and therefore there's a result that tells you that if you know these non-embedded quantum disks, then there's a unique way to weld them together, and this unique way to weld them together is going to give rise to an SLE curve. Right? So you have these independent structures, and then you force them to glue them together like a patchwork. Of course, it's not just a usual patchwork because it's a fractal patchwork with things going in all directions, plus, minus, everywhere. However, what happens is that the rule of how to glue together these non-embedded abstract surfaces is going to reconstruct for you the whole picture of the CLE with the Liouville quantum gravity on top of it. Now, I guess I'm over time. Well, not quite. I started 1 minute late, 5 minutes late because of introduction. I'm going to conclude, but I just want to say that this type of result. I mean, there are variants. You can do the same with half planes. You can also there are a number of variants. You don't need to do you can play with the asymmetry. You can put the bubbles to the right or to the left and things like that. But there are a number of results now on the planar maps, on the discrete structure point of view. So the idea is to say, working on the square lattice is too difficult. Maybe doing Ising model or percolation of square lattice is difficult, but maybe if we work on a lattice which is itself random on the discrete level by exploring these discrete planar maps, which are these random graphs, maybe things, if you choose them correctly, maybe there will be a nice Markovian type exploration structure there. And for those of you who have listened to Curien, Le Gall, and something, they like to call about the peeling process of how to peel a Brownian map, a planar map, and that's exactly the discrete analog of these type of things. Now, there's something called stable maps, and the stable maps or Boltzmann maps are supposed to correspond to scaling limits of something where you put a planar map, and on top of the planar map, you put an Ising model. And then instead of taking them independent, what happens is that you take the planar map with an additional Ising model, and then you take them in an annealed way. So you're going to give a bonus to those planar maps that have a higher partition function for the discrete model you look at. And those can be explored in a nice way. And from the discrete point of view, you see a number of formulas coming out. You have papers by Curien, Maillard, Mirmont, Bettinelli, I mean, all the French planar maps, strong people there. And what the general thing is that what comes out of that is that exactly these type of, you get to some formulas that mimic some of these objects here. You see the Poisson point process up there is very nice because one thing you can, for instance, define is the limiting area measure associated on the fractal carpet associated to that has to do somehow with the total mass of stuff you are discovering. And that gives exactly the same formulas that you can sort of see asymptotically from the discrete models. So ultimately, I mean, we are quite optimistic with Scott and Jason that this type of structure there is ultimately going to enable to pin down the fact that in the LQG story here, right, then there will be, try to, extract the existence of the metrics that are behind there. I mean, that's sort of one of the big goals of this thing. So this is not just a way to, hey, we can glue things. It has, probably it's likely to give a lot of insight also into what these structures are. And sorry for being over time, but it's always the luxury of having the break after you. Nobody's getting too nervous about the next talk. So thank you very much for your attention.